And I'm going to come up here on the back end of our time together today to talk to you a little bit about the test beds that we're working on with the SimCenter and give you some introduction to that workflow and how it might be beneficial for your work. So the test beds are really, I would say, a signature computational environment, an effort that we're undertaking at the SimCenter for some important reasons. I like to think of it as computational scaffolding, meaning we're linking together and creating a workflow that we truly hope over time the community will come and join as active developers so that we can improve the fidelity of our ability to model both wind hazards as well as their impacts on structures and the corresponding damage and losses. So what we're trying to do here is show how you can integrate some of the SimCenter tools you've heard about already, but also things that you might bring to the table into these workflows using this scaffolding. And I think it's really an exciting opportunity when you think about the test beds, because it's one of the few times in our research we get to see the end-to-end simulation. We get to see how hazard translates to damage and ultimately, losses and impacts on communities at large scale. And often we're very focused on our subassembly or our individual structure. But to link all that together takes expertise and contributions from a lot of members of our research community. So the test beds are both, ambitious and broad reaching, but they create a sandbox where we can all come play, and experts in modeling wind effects on structures can come play with those of us who are experts at modeling how our structures perform, can come play with those that have collected data on damage and loss. And when we play together, we can actually link all this together to do some pretty ambitious regional simulation. So it definitely will broaden the impact of your research to show how maybe your small part of this story is helping us to assess the regional impacts of something like a hurricane. And as you're going to see in my brief comments today, when we start to build these test beds, we really see the gaps, like what is missing in the data, the models, and the simulation tools. And that then informs the next generation of research and gives us new problems to work on as scholars. So I think the test beds bring it together. They also shine a bright light on the deficiencies that we have and help to guide our research going forward. And the really exciting part about a test bed is that because it's so tangible, it's real communities under these simulated events, they show real societal impact and they can be used by real decision makers. So you can actually start showing how our research translates to practice and starts to really get collaboration going around this idea of how we can assess the risk of things like hurricanes. So the SimCenter has a number of test beds that they previously released, and those were focused on earthquake hazards. I'm showing them here for just a quick glimpse, but I want to emphasize two things. One is the size and scale of these simulations. You were talking about hundreds of thousands, I think it was over 1 million parcels in the Bay Area simulations. And these were done at a parcel scale, so an individual building scale, not a census block. So this is kind of unheard of granularity, if you will, or resolution in these simulations. And that's thanks to the workflow as well as the access to high performance computing facilitated through the team at DesignSafe. So we can get to a point now where you could simulate a major natural hazard on an entire community at the building scale down to the component level performance. And that's pretty exciting. And you can do this in a way that swaps out the fidelity of different buildings in the test bed. So you really have flexibility as a researcher. But what I want to talk about today and kind of preview for this audience is the hurricane test bed, which, much like its predecessors for earthquakes, looks at creating some exciting places to come play, if you will, with our simulation models together. Now, we picked Atlantic City. It may not seem like the most glamorous location, but I want to explain why we picked Atlantic City, New Jersey. There was an existing project called NJ Coast that made available some very nice models and access to statewide data in New Jersey. And so as a result, as Frank said earlier, the SimCenter tries to reuse and repurpose developments from our community and get them stitched together in a way that they are accessible and usable for all of us to begin working together with. So we had some great opportunity there to use that. The other thing I'll note about what made this test bed really attractive is, as Hassan said earlier, wind hazards affect low-rise construction, especially wood frame residential construction, as David alluded to just now, all the way up to high-rise buildings who can have this, more dynamic response and issues related to even habitability. In Atlantic City, interestingly, you have all of those. You have the tall hotels and casinos down to the beachfront communities, and we can have that in all one unified test bed. So because of that, and this very nice distribution, as you can see in the slide here, of different typologies and ages of construction, it's actually a really attractive test bed to start asking the question of what would it take to bring this together for one unified simulation environment. So when we come over to hurricanes, what's exciting is the opportunity to look at intersecting and cascading hazards. Now we get to start exploring how we create a computational environment that can look at the response of wind, storm surge, and wave action. And what we want to be able to look at are those particular hazards because they are the ones that induce, demands and primary demands on the load path of the structure. I will note that we're not doing inland flooding in this particular test bed, nor are we explicitly modeling water penetration or other wind-driven debris, though I will of course highlight that those two important effects are included in the way that we approach damage and loss modeling as we move through the workflow. So our primary focus again from the hazard side is wind, storm surge, and wave action here in Atlantic City as our first test bed. Now what this slide shows you is how we have segregated the test bed into modules. And the idea behind this is that each module lets us step through how we describe the inventory, how we describe the hazard geospatially, how we then represent these buildings, if you will, in a computational environment, how we represent them, how we simulate their response to the hazards, and then how we estimate damage and loss across a large inventory. I'll step through briefly these 5 modules. And what I want to highlight is what we're doing is building out capabilities so that they have a low fidelity at level 1, but then showing you how we'll build out more capability at level 2 and so on, so that you have a variety of options in your simulation for how fine you want to resolve or at what fidelity you want to describe the building, the hazard, etc. So beginning with the way we describe assets, at level 1, we are working with tax data. Unfortunately, tax data is notorious for both being corrupted and incomplete, as well as missing critical information, in this case, about roof geometry. So what we do is we take the tax data from the state of New Jersey, and then we bring in some exciting tools developed by our AI team at the SimCenter to augment that data. And that same team is helping us at level 2 take what is just a simplified description of a building by attributes in a tax database and turn it into a 3D geometric model so we can actually start putting loads on the structure. And that means extracting from images the building surfaces and geometries so you can literally digitize a city. And the way this is being done is the SimCenter has, developed techniques to go into the tax records and basically extract out and mine all the information needed to build up these giant inventories through a querying process. And then by bringing a tool called Brails into the workflow, we are able to take street view imagery and satellite imagery and use image processing to mine the characteristics of those images so we can classify roofs as hip or gable or flat. We can pull out geometry so you can see the elevation of the structure for looking at storm surge. And we can even extract out the building surfaces and openings so you could literally digitize from a photo a building and bring it into the test bed. And so Brails is a really exciting AI tool to really help us marshal that effort and complete those incomplete and corrupted tax data. Now, once we come into the hazard characterization, we provide at level 1 and level 2 of the test bed 2 types of capability. At level 1, we have predefined scenarios. Basically, you have libraries of high fidelity historical and synthetic scenarios, wind fields, storm surge, wave run-up, for both a Cat 5 scenario hitting Atlantic City, as well as Superstorm Sandy. We also give you the ability to bring in hazard descriptions from prescriptive code and regulatory products. That would be ASC 7, as well as the FIRMs, the flood insurance rate maps. So think of level 1 as predefined scenarios. When we get into level 2, then you actually get to simulate yourself using high efficiency simulations where you can actually set the storm scenario you want to look at and generate your own wind field and storm surge to bring into the model. So level 2 is user defined simulations. But in both cases, we are using the land use land cover data and the topography, the DEM, from the local area, so it is an authentic simulation of the site-specific hazard characteristics that are then interpolated to the location of your building in the simulation. Now, when we get into the asset representation, our goal here is then to describe the building in a way that the damage and loss models can understand what the building is made of and therefore predict accurately the level of damage and loss to expect. At level 1, this is done through a simplified approach using the way HAZUS describes damage and loss in its current existing formulation. What this means is that every building that we now have in this giant inventory has to be assigned some attributes so they match the way HAZUS describes the building. So we take that parcel data and we develop a giant rules engine that looks at building codes and standards, industry trends, as well as even human behavior data, since we know mitigation is often a human decision, and year by year writes a rule based on the norms at that time. So every building is classified based on age of construction with the attributes that were most likely present at the time of its construction. And this lets us then have an inventory that is suited for analysis by HAZUS, again at the parcel level rather than the census block level. Of course, at level 2, things get much more exciting since we'll be able now to actually have three-dimensional representations of the building envelope so that we can actually put those pressures and loads onto the building surface and move them through the load path. And that means bringing up an important innovation in the SimCenter, and that is a data model that actually preserves all those three-dimensional dependencies and all that information in a concise way so it moves efficiently through the simulation. Now for response simulation, what we're doing in level 1 is actually nothing. And the reason for this is that the hazard is described in a way in HAZUS that it maps it directly in terms of wind speed over to its damage and loss library. And there is no need for any kind of engineering demand parameters, response of any form to make that relationship happen. And so as a result, there is no load response, if you will, no response to the applied loading in level 1. But in level 2, we're bringing the capability to start bringing in a form of structural evaluation, if you will, through a fault tree analysis that allows us to map pressures onto the building surface, both the storm surge as well as the wind field, and then be able to move through the fault tree analysis to take a look at how that would propagate through the system and create the kind of cascading losses that you would expect, especially associated with breach of the building envelope. So we'll be able to move into those critical dependencies for mapped pressures. And by the time we arrive at the damage and loss simulation, at this point in level 1 fidelity, we'll again be using HAZUS directly. And those descriptions of vulnerability as captured in HAZUS, they have been taken from the current format in the HAZUS database and fit with normal or log normal CDFs so they can be more efficiently stored and so that damage can be explicitly mapped to losses. And this gives us the opportunity then, through a tool called Pelican, which Adam will talk about more tomorrow, to build in over 3,000 configurations in HAZUS into one singular tool that can actually apply those across the inventory effectively. And as we move into level 2, we're just going to increase the fidelity and resolution of that representation. And that means moving us to component-based descriptions of damage that will let us again start accounting for the losses driven by wind and storm surge separately and combining those in a rational way to predict the overall impact or losses on the whole building itself. Pelican as a tool, again, as I mentioned, is pretty exciting because it is migrating in all of the damage and loss data that is currently present in HAZUS to give you the ability to evaluate that at a parcel level. Currently, there's a database of over 8,000 building and component files that have been brought into Pelican. And what we're doing in Pelican is finding ways to actually build that out so that we can represent earthquakes, hurricanes, buildings, and even lifelines in one uniform application that can be integrated into these regional simulations using the tool RWhale. So really Pelican is going to be one of the most critical features, and again, something that Adam will engage tomorrow, where we'll have a more in-depth discussion of how to imagine the capabilities Pelican should deliver, especially for wind hazards. And RWhale, as I mentioned, is the tool that supports the execution of these regional workflows. It gives you the ability to execute these simulations for these large regions. And again, you can do a small subset of your test bed for a small scale simulation on your local computer. but more importantly, you can have access in the cloud-based version to run this large-scale simulation. Again, these data sets for Atlantic City, it's 80,000 buildings roughly. For the other earthquake ones, they were in the hundreds of thousands of, I think, over 1 million individual parcels executed using high-performance computing through DesignSafe. And RWill gives you the capability of executing those kinds of analyses with all of your data curated then on DesignSafe in the data depot. And as Frank mentioned earlier, and I want to close on this, you don't have to be a wizard in executing these workflows, because the whole point of the SimCenter is to create the interfacing, the preprocessor and the post-processor, that takes these little modules I introduced in this brief presentation and links them together, interfaces them with the appropriate supporting databases, and links them also to uncertainty quantification tools so that you can run these workflows, assemble, supervise, and execute them in a way that's accessible and feasible for the user. And as Hassan alluded to in his talk, the front end that's provided by the SimCenter lets you, for each step in this puzzle piece, each chain here, come in and select from the front end the level of resolution or fidelity you want, or the various tools that you want to plug in. So I might run my simulation at level 1 across all of the modules except for the hazard, where I want to do the level 2 fidelity and run my own custom simulation. I can build a tool chain that allows me to make those customizations in the modules as I desire, and then using that same beautiful interface, make the decision whether I execute that locally or push it out to DesignSafe. So I would say that while these test beds are ambitious and quite exciting, you don't need to have fear about the ability to approach it, because the front end helps you manage that, and the back end tools are there to make it possible, including linking you to HPC. So that when you come in and run the Atlantic City testbed, now you can see at individual parcel scales the damage that would be sustained, in this case under the Cat 5 scenario, as well as the mean loss ratios one might expect in each of those parcels along this coastal community. So this was a quick run through, and we shifted the time a bit, but I'm thankful for your patience. What I want to close with is just to remind you, the goal of this is to democratize access to these kinds of tools for our community, to lower the bar to come and use these kinds of tools and to come together to collaborate. Everything I've alluded to here, which we will be releasing with more engagement of this community of wind engineers, but also the wider NHERI community, it's available at DesignSafe and in the GitHub repository. This is all open, and the intent is to be shared and used among our community. And I really want to emphasize this is community-driven software development. While we're linking this together to get that scaffolding in place, the goal is the work you're going to do here with the Wall of Wind and with the SimCenter should be able to, if you desire, contribute back to improving the capacity, the fidelity of this simulation environment, so your research can be integrated into these grand test beds to demonstrate how your contribution is changing the way that we are able to simulate and evaluate the risks to coastal communities.